survive. For tens of millions of years, nature never stopped creating increasingly formidable prehistoric creatures. This was the Permian, a world of fierce struggles before the age of dinosaurs. Around 250 million years ago, what is now South Africa grew hot and arid. Rivers and lakes dried up, leaving the earth cracked beneath swirling clouds of red dust. Near one of the few remaining watering holes, an old Scutosaurus slowly stepped away from its herd. Thick armor covered much of its body, protecting it from many dangers that had once roamed these plains. But age had made every step slower, and the long walk beneath the relentless sun had drained its strength. For a brief moment, the silent landscape seemed perfectly peaceful. But it wasn't. Concealed among the scattered bushes, another pair of eyes had been watching for a long time. Innistransevia remained perfectly still. It didn't rush forward. It didn't waste energy. The giant predator waited until the Scutosaurus lowered its head to drink. Then, in a sudden burst of speed, it charged. The Scutosaurus reacted immediately, turning its armored body toward the attack. Thick, bony plates protected much of its neck and shoulders, forcing the predator to change its strategy. Instead of continuing to push toward the neck, the Innistransevia shifted its attack, driving the larger animal off balance before targeting one of its hind legs. The struggle lasted for several exhausting minutes before the massive herbivore finally collapsed. The hunt was over, but victory brought little relief. The Innistransevia stood beside its meal, breathing heavily. Every successful hunt now demanded nearly everything it had left. Looking across the drying lake, there were no large herds waiting nearby, no signs of another easy meal, only silence, dust, and a landscape that seemed to be growing emptier with every passing season. This was one of the most successful prehistoric creatures of its time, yet even it was beginning to struggle. If evolution had created such an extraordinary hunter, why was its world falling apart? To answer that question, we have to travel back nearly 50 million years to when the first great rulers of the land began to emerge. Subscribe now because this is only the beginning of an extraordinary story. The world was recovering from an earlier chapter of Earth's history. Pangaea had recently formed, joining nearly all of the planet's land into a single supercontinent. Vast wetlands stretched across the landscape. Food was abundant, and for many plant-eating animals, life had never looked more promising. Among the most successful was a sturdy herbivore called Diadectes. Every day, herds wandered slowly through the lush vegetation, feeding almost constantly. With plants everywhere, there was little reason to compete. Young Diadectes grew quickly, while adults reached impressive sizes. For a time, it seemed like a world where large herbivores had almost nothing to fear. But nature rarely allows abundance to remain unchallenged, and evolution was already beginning to reshape the world. Like most animals of their time, Diadectes relied on the sun's warmth before becoming fully active. Still sluggish from the night, the herds moved slowly through the vegetation, with the young staying close to the adults as they searched for fresh plants. But another predator had been awake long before dawn. Without warning, it burst into the open. The herd scattered in every direction as the predator charged. It ignored the largest adults and went after the smaller members of the herd. Instead of chasing the entire herd across the open ground, it closed the distance in only a few powerful strides before clamping onto the side of its struggling prey. Its name was Dimetrodon. Long before the first dinosaurs appeared, Dimetrodon had already become one of the most successful predators on land. Yet its greatest advantage was not simply its powerful jaws or sharp teeth. Rising above its back was a remarkable sail, supported by long neural spines. For decades, scientists have debated all of its possible functions, but one of its greatest strengths was likely helping the animal absorb heat more quickly after sunrise. While many other animals were still waiting for their bodies to warm, Dimetrodon could begin moving earlier, giving it a valuable advantage during the coolest hours of the day. In a world where every opportunity mattered, being active just a little sooner could mean the difference between finding a meal or going hungry. The climate became warmer. Wetlands that had once stretched across the lowlands began to shrink, leaving behind patches of dry ground. Dense forests gradually opened into broad, drier plains. As the environment changed, so did the animals that lived in it. Dimetrodon herds became more scattered as food grew harder to find. Herbivores were forced to travel farther in search of vegetation. Instead of finding dozens of potential meals in a single valley, a predator might now spend days searching for one opportunity. For Dimetrodon, every hunt became far more challenging as the climate grew increasingly harsh. Success now depended on traveling greater distances and sustaining longer pursuits across the open landscape. Many hunts ended without success. Each failure meant valuable energy lost beneath an increasingly harsh sun. As food became harder to obtain, more and more Dimetrodon likely failed to find enough to survive. Their numbers gradually declined, not because they suddenly became weak, but because the world that had once favored them was disappearing. Nature had not rejected Dimetrodon. It had simply begun rewarding different abilities. As one survival strategy became less effective, evolution started testing new solutions. Among the predators that appeared during this changing world was Sphenacodon. At first glance, it looked remarkably similar to Dimetrodon, but one feature was immediately missing. The enormous sail had disappeared. Instead, its body revealed a different design. Its neck was thicker, its shoulders more powerful, and its muscles were built for strength rather than display. With a stronger bite and a sturdier frame, Sphenacodon was likely better suited to hunting across the increasingly open landscape. Yet predators were not the only animals being reshaped by the changing climate. Plant eaters faced an entirely different challenge. As rainfall declined, many soft plants became less common. Tougher vegetation began spreading across the landscape. Finding food was no longer the greatest challenge. Digesting it was. One herbivore met that challenge in its own remarkable way. Edaphosaurus did not compete with predators through speed or armor. Instead, it adapted to survive on plants that many other animals struggled to eat. Its jaws became stronger, allowing it to process tougher vegetation more efficiently. Although Dimetrodon and Edaphosaurus looked surprisingly similar from a distance, they represented two completely different paths through evolution. One refined the skills of a predator, the other mastered the life of a peaceful grazer. Across the Permian, countless species were changing alongside their environment. Some evolved into stronger hunters, others developed entirely new diets. Evolution was no longer preserving yesterday's winners. It was searching for the species best suited for tomorrow. And no one, not even the most successful animals of their time, could know which path would ultimately endure. By the Middle Permian, life had become far more demanding. Finding food was no longer easy. Evolution no longer favored only the fastest predators, but those that could solve new challenges. One predator seemed ready for that challenge. Ankylosaurus was among the largest hunters of its time. Measuring nearly 16 feet in length and weighing close to 1,100 pounds, it possessed a massive skull supported by a powerful neck and muscular shoulders. For years, scientists envisioned this prehistoric creature as a slow-moving giant that relied primarily on brute force. But modern CT scans of its skull have revealed a very different picture. Its inner ear was surprisingly well developed, suggesting excellent balance and coordination. The structure of its skull also points to sharp vision and quick head movements. Those abilities will soon be put to the test. As the evening sun sets over a vast, arid plain, a herd of Tapinocephalus gathers near one of the last remaining water sources. Adults weighing well over 2,000 pounds surrounded the younger animals, forming a living wall of thick bodies and reinforced skulls. Every movement was deliberate. They had learned that surviving in the Permian often depended on staying together. But they were not alone. Ankylosaurus had already been watching for some time. It made no move to attack. The largest adults were simply too dangerous to confront head-on. Instead, the predator circled slowly around the herd, waiting for a mistake. Minutes passed. Dust drifted across the plain. The young remained protected behind the adults. Then, everything changed. One juvenile wandered only a few steps farther than it should have. The moment it saw an opening, Ankylosaurus charged. The massive adults charged to defend the herd. The predator reached the young first, but before it could strike, a giant Tapinocephalus rammed into its flank with tremendous force, sending both animals crashing off balance. For several tense moments, neither side gained the advantage. Ankylosaurus searched for another opening, but every path was blocked by another adult stepping forward to protect the herd. One by one, the defenders closed the gap around the juvenile until the opportunity disappeared completely. In the end, the predator backed away and abandoned the hunt. Across the Permian, herbivores were no longer relying only on size. Living in groups, protecting their young, and standing together had become powerful survival strategies. But evolution never stops. Millions of years passed and the Permian continued to change. The climate grew even hotter. Seasonal droughts lasted longer. New herbivores appeared, each carrying a different answer to the growing challenges of their world. Among them was Scutosaurus. Standing nearly 9 feet long and weighing well over 2,000 pounds, Scutosaurus was built like a walking fortress. Thick, bony plates were embedded throughout its skin, covering much of its shoulders, back, and neck. It was not fast, and it could never outrun a determined predator. Instead, it relied on something far more effective. It made itself incredibly difficult to bring down. By this time, the great predators of the late Permian had also changed. The descendants of earlier hunters no longer depended on overwhelming strength alone. They had become faster, more precise, and far more specialized. A massive predator quietly stalked a lone Scutosaurus, making its way toward a shrinking waterhole. It waited for the perfect moment before launching its attack. The predator was simply too powerful. Scutosaurus had little chance of escaping. It was an endless race with no permanent winner. Yet while giant predators and armored herbivores competed across the open plains, another group quietly chose a completely different path. These small dicynodonts never try to outrun the fastest predators. They do not develop heavy armor or powerful horns. Instead, they escape danger before it ever arrives. As temperatures climbed during the day, they disappeared into underground burrows where the heat was less intense and predators rarely followed. Their strong beaks allowed them to feed on tough, low-quality plants that many larger animals ignored. They were not the strongest. They were not the fastest. They simply asked a different question. Instead of wondering how to win the next confrontation, they evolved to avoid it altogether. Looking across the Permian, evolution was experimenting with every possible strategy. Some species grew larger, some became faster, some built armor, others relied on cooperation, and a few survived by staying out of sight. No one could know which path would shape the future, but before long, nature would reveal an answer that no species could have anticipated. Millions of years passed, and the Permian continued to shape its predators. Some became lighter, others covered greater distances with less effort. Their legs grew longer, their movements became faster, and their senses sharpened. Among them was a group known as the Gorgonopsia. These predators began to change the survival strategies of prehistoric creatures in the Permian period. They no longer relied on overwhelming size alone. They depended on timing, precision, and speed. Generation after generation, those qualities continued to improve until one hunter stood above all the rest. Its name was Inostrancevia. At nearly 12 feet long and weighing close to 900 pounds, this prehistoric creature was one of the largest and most specialized predators that the Permian period ever produced. As the first light reached the open plains, a herd of Scutosaurus slowly made its way toward one of the last dependable lakes. Far behind the herd, another journey had already begun. Inostrancevia had been following their tracks since before sunrise. The growing heat made every step more exhausting, but the predator showed remarkable patience. It was not searching for the strongest animal. It was waiting for the right moment. By late afternoon, the opportunity finally appeared. The oldest Scutosaurus drifted farther behind as the rest of the herd continued toward the lake. A narrow gap opened between the aging herbivore and the others. It lasted only a few seconds, but that was all the hunter needed. Inostrancevia burst forward with incredible speed. Dust filled the air as the two giants struggled across the dry ground. The Scutosaurus swung its massive body from side to side, trying to throw the predator off balance, but every movement cost precious energy. Inostrancevia never wasted its own strength. It held its position, adjusted with every step, and waited for exhaustion to do the rest. Slowly, the giant herbivore lost its footing. The struggle ended almost as quietly as it had begun. It was a hunt built on patience and precision. After nearly 50 million years of evolution, longer legs, a flexible body, and saber-shaped canine teeth had made it one of the late Permian's most formidable predators. Standing beside its meal as the evening sun sank toward the horizon, Inostrancevia looked every bit the ruler of its world. Nothing around it appeared capable of taking that place away. The greatest predator the Permian had ever created had reached the height of its success. But the world that had shaped it was beginning to disappear. For millions of years, life had adapted to every challenge the Permian could offer. Predators became faster. Herbivores became stronger. Every generation found a new way to survive. But this time the enemy was the planet itself. Far to the north, an immense volcanic province erupted again and again. Rivers of lava covered the land for hundreds of thousands of years. Each eruption poured enormous amounts of carbon dioxide, sulfur dioxide, and other toxic gases into the atmosphere. The sky grew hazy. Acid rain fell across vast regions. Temperatures climbed higher than anything life had experienced before. The warming did not stop. As the great herds declined, predators soon followed. Successful hunts became rare, not because they had lost their strength, but because there were fewer animals left to hunt. Entire food chains that had taken millions of years to evolve began falling apart. The oceans fared no better. Warmer water held less oxygen, creating vast dead zones where marine life could no longer survive. Ancient reefs collapsed. Countless fish, shellfish, and other sea creatures disappeared. In places, oxygen vanished so completely that bacteria released poisonous hydrogen sulfide, turning parts of the ocean into toxic waters and poisoning the air above them. Nowhere was untouched. Forests fell silent. Rivers carried fewer signs of life. Every year brought fewer young, fewer survivors, and fewer species. Animals that had ruled the earth for millions of years disappeared, one after another. Then came the final collapse. Entire ecosystems unraveled in what was, geologically speaking, only a brief moment. Around 90% of marine species vanished. Nearly 70% of vertebrate species on land disappeared. It was the greatest mass extinction the planet has ever known. When the worst had finally passed, the Permian was almost unrecognizable. The great forests were gone, countless rivers had vanished, and many of the giants that had once ruled the land would never return. For a long time, the world seemed almost empty. Yet life was not finished. Among the survivors was a small, unassuming animal called Lystrosaurus. It was not the fastest. It was not the strongest. It had no massive claws or long saber teeth, but it possessed something far more valuable. It could dig deep burrows to escape the heat, survive on little food, and feed on tough plants that many other animals ignored. In a world where almost everything had been lost, those simple advantages became the key to survival. Before long, Lystrosaurus spread across much of the recovering world. The age of giants had ended, and a new chapter had quietly begun. The greatest lesson of the Permian was now impossible to ignore. Nature does not always reward the strongest. More often, it rewards those that can adapt when everything around them changes. They would eventually become the first true mammals, beginning a journey that would continue long after the Permian had faded into history. If the Permian teaches us anything, it is that no king rules forever. The prehistoric creatures that survived this catastrophe would soon give way to an entirely new dynasty. This new lineage dominated the Earth for over 100 million years. It was the age of dinosaurs. So be sure to subscribe and join us as we explore the incredible world of the dinosaurs in the videos ahead. Thank you for watching, and we'll see you next time. Could what we've known about the appearance of the prehistoric world for the past century be a great misconception? What if the most terrifying monsters of the Jurassic period didn't have the cold, scaly skin we've always believed? For over a century, humanity has shaped the appearance of those who once ruled this planet through their skeletal remains. We envisioned creatures with rough, gray, scaly skin, but all those conventions crumbled in Liaoning, northeastern China. This is not just the site of fossils, but the place that changed our definition of ancient life. The mystery of the feathered dragons. Why have these delicate, easily decomposed hairs survived intact for 125 million years? The answer lies in this video, as the veil of the past is lifted, revealing the secrets hidden within each fossilized cell. In 1996, a broken slab of rock fractured an entire paleontological historical structure. From within the rock emerged Sinosauropteryx. It wasn't a bird, but a carnivorous dinosaur. However, instead of reptilian scales, its entire body was covered in a thick, fine layer of downy feathers. The presence of Sinosauropteryx was the strongest evidence yet to confirm that the term feathered dinosaur was no longer a work of fiction, but a real biological fact. To understand why the discoveries in China were so groundbreaking, we must go back more than a century to the quiet limestone quarries of Solnhofen, Germany. There, a solitary secret was once held, an organism that sparked the longest-running debate in paleontological history. In 19th century fine limestone quarries, a bizarre fossil, Archaeopteryx, has been unearthed. This creature exemplifies the concept of mosaic evolution. Despite possessing the perfect feathered wings of a bird, its skeleton exhibits the pure characteristics of a carnivorous theropod dinosaur, with sharp teeth, claws on its wings, and a long bony tail. Specimen number 11, found in 2011, even shows that feathers covering it down to its feet were a biological feature that helped it reduce drag and retain heat, something that typical reptiles lack. It was Thomas Henry Huxley, a brilliant biologist, who pioneered a bold hypothesis that birds are direct descendants of carnivorous dinosaurs. He based this on striking similarities in their bone structure. However, this view sparked a fierce intellectual battle within the scientific community. His opponents argued that the similarities were merely coincidental and refused to accept the possibility of these colossal creatures being related to delicate birds. The impasse began to drag on for over 100 years, during which time Archaeopteryx remained the only evidence. In the eyes of paleontologists at the time, it was considered an outcast, an evolutionary anomaly rather than an ancient link. The lack of other intermediate species led to Huxley's hypothesis being dismissed, as science could not accept a theory based on a single individual. Why was the fossil record so long interrupted? Because bone is a hard mineral, while feathers are soft keratin, which decomposes easily. Typically, environments strong enough to preserve bones also oxidize too quickly, causing feathers to disappear completely before leaving a trace. This curse was only broken in 1996, when ultrafine volcanic ash deposits in Liaoning, an oxygen-deficient environment, froze time, preserving even the thinnest feathers intact, officially opening the continuous chain of evidence that humanity had been searching for in vain. To understand why feathers exist, we must know the environment in which they lived. Geologist Romain Amiot conducted a sophisticated chemical analysis, measuring the ratio of oxygen isotopes in fossilized tooth enamel. The results overturned all preconceptions. In Liaoning 125 million years ago, the climate was not hot and humid, but rather had harsh winters with heavy snowfall. This icy context transformed feathers from decorative objects into a necessary survival tool. So what did these plumes look like? For over a century, color was something time had erased, until paleontologist Xu Xing discovered melanosomes. These weren't living organisms, but rather tiny pigment sacs preserved in volcanic ash. Using an electron microscope, he deciphered the code of their shapes. Sausage-shaped sacs yielded black, while round sacs contained red-orange. For the first time, humanity could reconstruct the actual appearance of dinosaurs based on physical evidence rather than imagination. The combination of insulation and vibrant pigmentation leads to a compelling conclusion. These are warm-blooded creatures. Maintaining such an intricate and brilliant plumage is an expensive energy gamble. Only an extremely efficient metabolism can simultaneously generate heat to withstand the cold and provide enough nutrients to nourish these sharp feathers. The feathers are the thermoregulatory system that allows them to maintain a constant hunting intensity, a privilege that cold-blooded species never possess. Look at modern birds today. The way they use their plumage to attract mates or intimidate rivals is a perfect replica of survival tactics from 160 million years ago. Completely different from the commonly seen image of a scaly tyrant, Yhcum is a testament to the breaking of the limits of feather size. Weighing 3,300 pounds, it didn't use its bare skin for cooling like other giant tropical dinosaurs. Instead, it covered itself in a thick layer of feathers up to 6 inches thick. This feather layer didn't have the structure of modern birds, but resembled a long, dense mane of hair, covering it from the top of its head to its tail. The core difference lies in the function of this fur as an energy regulator. It allows a giant warm-blooded creature like Yhcum to maintain an extremely high metabolic rate and muscle flexibility even when ambient temperatures drop below freezing at 32 degrees Fahrenheit. It is this distinctive fur that makes it the absolute ruler of frigid lands, where ordinary scaly reptiles would be paralyzed by heat loss. In stark contrast to the giant Yhcum was Anchiornis, a tiny entity the size of a pigeon, yet possessing an extreme optimization of evolution. The difference lay in Anchiornis's feathering, which extended not just down its body, but in dense, long flakes from the top of its head to its toes. This was a precise mechanical calculation. A tiny body with a large surface area on all 4 limbs maximized air resistance. Instead of simply retaining heat, this dense feather structure transformed Anchiornis into a perfect prototype for aerodynamics. It represented the point where feathers ceased to be merely a warm covering and became a tool for locomotion, allowing these tiny creatures to perform leaps and glides through space, the final stepping stone before true wing development. Before the feathered dinosaurs took flight, the skies belonged to the pterosaurs. Masters like Germanodactylus dominated with their delicate yet agile membranous wings. The intense competition from these sophisticated flying machines forced smaller dinosaurs into a difficult situation. Either submit to the ground or find entirely new ways to fly in order to survive. The most striking link in this race was Microraptor. This dinosaur possessed a structure of 4 long feathered wings growing on both its forelimbs and hind limbs. Instead of gliding like modern birds, Microraptor used its feathered legs as a pair of auxiliary wings for lift and navigation. This was a bold experiment of nature, proving that the evolutionary path to the skies was not a single one, but full of bizarre variations. To truly conquer the skies, dinosaur bodies underwent a radical mechanical restructuring through pneumatization. The dense, heavy skeletal frameworks gradually transformed into a hollow system with tiny internal lattice-like partitions. Reducing weight by up to 70% while maintaining exceptional durability. A key element of this bioengineering was the fusion of the clavicle into the V-shaped furcula, acting as a kinetic energy storage system, releasing powerful thrust with each wing beat. Cruel elimination. Why do birds survive? The final confrontation between pterosaurs and feathered dinosaurs, the ancestors of birds, was decided by the superiority of feathers. When disaster struck, the pterosaur's membranous wings were too sensitive and difficult to repair, while feathers, with their individual fiber structure, not only allowed for more efficient flight, but also provided protective armor, insulation, and were easily replaceable. As a result, pterosaurs disappeared, while feathered dinosaurs overcame the narrow path of survival to become the modern birds we know today. The KPG catastrophe, a violent purge. 66 million years ago, a meteorite impact ended the age of giants. A thick dust cloud obscured the sunlight, causing a chain reaction of collapses in the global food chain. In that extinction scenario, enormous creatures with massive energy demands had no chance. The world was left with only those possessing compact size and the ability to move nimbly between ecosystems. It was these tiny, feathered dinosaurs, once forced to evolve into flight, who were the only ones to slip through the narrow window of extinction. From a small group of survivors of the catastrophe, they evolved and diversified into over 10,000 modern neonith species of birds. From ocean-going seabirds to garden songbirds, all carry within them the blood and genetic code of these prehistoric predators. The truth is, dinosaurs never truly went extinct. They didn't disappear, they simply transformed to adapt to a new world. When you see a bird soaring through the sky, you're witnessing the living legacy of an empire that once ruled this planet.